Let us now see an application about a projectile. So we have a projectile that is fired with angle of elevation alpha and initial velocity vector v naught, and we're asked to find the range of the projectile, the value of the angle of elevation alpha that maximizes the horizontal distance traveled, the maximum height reached, and the speed at impact. Now, first of all, we have to set up the axis so that the projectile starts at the origin. So we have here the x-axis, the y-axis, and the projectile starts at the origin. The projectile has an initial velocity vector, vector v naught, and an angle of elevation alpha. Since the force due to gravity, let's call that force due to gravity vector F capital, acts downward, we'll have that this force vector is equal to the mass of the projectile times the acceleration vector, and that is equal to the negative, since that force acts downward, of the mass times the gravitational acceleration times the vector j. And here the gravitational acceleration is equal to the magnitude of the acceleration vector, and this is approximately equal to 9.8 meters per second squared. Therefore, the acceleration vector at any time t is given by the negative g times the vector j, and therefore the velocity vector at any time t will be given by the integral of the acceleration vector times dt. So that is equal to the integral of negative g times j times dt, which gives us that it is equal to negative g times t times the vector j plus some constant of integration c. We are given that the projectile has an initial velocity. So the velocity vector at time t equals to 0 is equal to the vector v naught. So that is equal to the constant of integration c. And therefore, the velocity vector is given by the negative g times t times the vector j plus the initial velocity vector v naught. Now, integrating again the velocity vector will give us the position vector, vector r of t, that is equal to the integral of the velocity vector times dt. So that is equal to the integral of the negative g times t times the vector j plus the vector v naught times dt. So this is equal to the negative 1/2 g times t to the square times the vector j plus vector v naught times t, and then plus some constant of integration d. Since the projectile is fired from the origin, then that means that the initial position of the projectile is given by the velocity, by the position vector r at t equals to 0. So that is equal to just a 0 vector, since the projectile is fired from the origin. So this is equal to the integration constant d. Therefore, the position vector of the projectile will be given by the vector r of t, that is equal to the initial velocity vector v naught times the times t, and then we have minus 1/2 g times t to the square times the vector j plus the 0 vector, which corresponds to the constant of integration. So that is equal to the vector v naught times t minus 1/2 times dt to the square times the vector j. Now let us denote the initial speed of the projectile. So we have the initial velocity of the projectile is given by the vector v naught, and let's now denote the initial speed of the projectile, which is given by the magnitude of the initial velocity to be equal to just v naught. Then from the triangle, from this triangle, we have that the initial velocity vector, vector v naught, will be equal to the x component, which is equal to v naught times the cosine of the angle of elevation alpha times the vector I, plus the y component. So we have that the x component is equal to v naught times the cosine of the angle alpha, and the y component is equal to v naught times the sine of the angle alpha. So that y component also projects here. So we have v naught times sine of the angle alpha times the vector j. And therefore, the velocity vector at any time t is given by the vector v naught minus g times t times the vector j, and this is equal if we express the initial velocity vector v naught with respect to its x and y components, we'll have v naught times cosine of the angle alpha times the vector I plus v naught times sine alpha times the vector j minus g times t times the vector j. And if we combine the I and j components, we'll have that the velocity vector v of t is equal to v naught times cosine of alpha times the vector I plus v naught times sine alpha minus g times t times the vector j. So the vector equation, the position vector of the curve becomes, since we have this velocity vector and also we have expressed the initial velocity by its components, we'll have that the position vector RT is equal to the vector v naught, which we can take from here. So we have, this is the position vector, and we now express the vector v naught in terms of the x and y components. So that will give us, let us write first of all, the vector v naught times t minus 1 half g times t to the square times the vector j. So that is equal to v naught times cosine of the angle alpha times the vector I plus v naught times sine alpha times the vector j and all that times t minus 1 half g times t to the square times the vector j. So that gives us that the position vector r of t is equal to v naught times cosine alpha times t times the vector I. And then we have plus, this is for the x component, and for the y component, we have v naught times sine alpha times t minus 1 half g times t to the square times the vector j. So this is the x component of the position vector, and this is the y component of the position vector. Therefore, we can derive the parametric equations for the trajectory of the projectile. So the x parametric equation will be that x is equal to v naught times the cosine of alpha times t, and y will be equal to v naught times sine alpha times t minus 1 half g t to the square. So let us now try to find one by one what is asked in the questions. For the first question that asks to find the range of the projectile, the range of the projectile means what is the horizontal distance. So the range is the horizontal distance that the projectile travels until it reaches again the ground. And to find that, we'll need to set y to be equal to 0. So when the projectile reaches again the ground, its height will be equal to 0. So x gives us any time the horizontal distance that the projectile has traveled at any time t, and y gives us the height of the projectile. So setting y to be equal to 0, that will give us that v naught times the sine alpha times t minus 1/2 g times t to the square is equal to 0. So from that, if we factor t, we get t times v naught times sine alpha times sine alpha minus 1/2 g times t is equal to 0. So that gives us that either t is equal to 0, or that v naught times sine alpha minus 1/2 g times t is equal to 0. So that gives us that the height is equal to 0 either initially before the projectile is fired, or when the time t is equal to 2 times v naught times sine alpha divided by g. So this is the time that the height is equal to 0 before the projectile is fired. And this is the time that the projectile reaches again the ground. Therefore, in order to find the whole range of the projectile, we have to take the parametric equation that gives x. So x is equal to v naught times cosine of alpha times t, and substitute t with 2 times v naught times sine alpha divided by g. So that will give us v naught times cosine alpha times 2 v naught times sine alpha divided by g. So this is equal, if we combine here, we'll have v naught to the square times 2 sine alpha cosine alpha divided by g. Therefore, the range, let's call that range d, will be equal to v naught to the square. Now, 2 sine alpha cosine alpha is equal to sine of 2 alpha divided by g. So this is the range of the projectile. V naught to the square times sine 2 alpha divided by g. The second thing that we're asked is the value of the angle of elevation alpha that maximizes the horizontal distance traveled. So we actually need the value of alpha that maximizes the range. So we see that the range takes its maximum value when the sine of 2 alpha, maximum value of range, when the sine of 2 alpha is equal to 1. So all other quantities are constant here. The only thing that can change is the sine 2 alpha, and it takes its maximum value that is equal to 1, and then in that case, the range will be maximum. So sine 2 alpha should be equal to 1, which means that 2 alpha is equal to pi over 2, and therefore alpha will be equal to pi over 4. So the angle of elevation that maximizes the horizontal distance traveled is equal to pi over 4, is equal to 45 degrees. Now for the third question, we have we are asked what is the maximum height reached, and for in order to find what is the maximum height reached, then we have to take the derivative of the height and set that to be equal to 0. So we have to take the parametric equation of the height and set that equal to 0. So we'll have that the derivative of the height with respect to t is equal to 0. And therefore, we need to take the derivative of v0 sine alpha times t minus 1/2 gt to the square. Take the derivative of that and set that to be equal to 0. So that will give us v0 sine alpha minus gt equals to 0. And therefore, the height is maximized at the time t that is equal to v naught times sine alpha divided by g. Therefore, the maximum height can be found by setting to the parametric equation of y t equals to v naught sine alpha divided by g. So that will give us v naught sine alpha times v naught sine alpha divided by g minus 1/2 g times v naught sine alpha divided by z to the square. So that is equal to v naught to the square sine squared alpha divided by g minus 1/2 v naught to the square sine squared alpha divided by g. So this is equal to v naught to the square sine squared alpha divided by 2g. Therefore, the maximum height that is reached is equal to v naught to the square times sine to the square alpha divided by 2g. Now, for the fourth question that asks to find the speed at impact, from the first part, the impact occurs at the time t that is equal to 2 times v naught times sine alpha divided by g. So this is what we have found in the first part. And substituting that to the velocity vector equation, we have that the velocity vector is equal to v naught times cosine alpha times the vector I plus v naught times sine alpha minus g times t times the vector j. So substituting this t over here, that will give us that the velocity vector at the time 2 v naught sine alpha divided by g is equal to v naught cosine alpha times the vector I plus v naught sine alpha minus g times the time t, which is equal to 2 times v naught times sine alpha divided by g times the vector j. So this is equal to v naught cosine alpha times the vector I minus v naught sine alpha times the vector j, if we simplify. And therefore the speed is equal to the magnitude of the velocity vector at time t. Let's write that explicitly, that time t, which is equal to 2 v naught sine alpha divided by g. So this is equal to the square root of the sum of the squares of the components of the velocity vector. So it will be equal to the square root of v naught cosine alpha to the square plus the negative v naught sine alpha to the square. So this is equal Now we have the square root, and we have a common factor of v naught to the square, and then we'll have inside a parenthesis cosine squared alpha plus sine squared alpha to the square, not to the square, just cosine squared alpha plus sine squared alpha. So this is equal to 1, what we have inside the parentheses. So that will give us the square root of v naught to the square, which is essentially equal to v naught. So therefore, the speed at impact is equal to the magnitude of the initial velocity. So the speed at impact is equal to the magnitude of the initial velocity.